Earthquake resistant construction. How does earthquake affect buildings? As we know that the concrete is a rigid material and it acts stronger under compressive loads and weaker under tensile load. Thus, earthquake generally refers to shaking of Earth's surface creating seismic waves, and when these seismic waves hit the structure, it produces shaking. And if the structure is rigid, like brick, masonry, and concrete, then it would have a damageful effect and will be near to be fallen. Now, a figure is shown in the screen. It shows that the effect of inertia in a building when shaken at its base. Now, there is a thing to remind you of that how the inertia affects the building and the structure made by man. Inertia is basically a law of physics. Effect of inertia generally amplifies the effect of external forces, leading to increased stress and strain on the structure. When these seismic waves hit the structure and it shake its base, these seismic waves will then be amplified by the inertia and will lead to the great damage. These figure shows that how the masonry structures and the concrete structures are damaged by the seismic waves or the earthquake. How can we protect the lives of those in danger? We must design buildings that can survive earthquakes. Site conditions. These site conditions shows different situations. First one is that where we have the compacted soil. These arrays are the sensors which determine the densification of the soil in the given reference point or the given layer. When these sensors having arrays are vertically downward and in the perpendicular situation, then we have seen that there is no shaking or there is no damage to the structure. When then we have stiff cohesive soil. Cohesive soil means that there is a large cohesion in the soil, means that it has greater quantity of water in it, but it is stiff. Stiff means it is compacted or it has a strong behavior towards the shaking. Then we have a groundwater table, and afterwards the water table we have a declining arrays. This shows that the structure will not be stable in this region. Number second, we have there a reinforced concrete wall. There we have a slopy array. These slope arrays denotes that the structure will be stable, and then moving further downward we will say we will have a smooth curve along these slope arrays. We will have when we have these curve arrays, we will have unstable, and we can say the construction here is not stable for living purpose. And then we have loose sand, and then dense sand and very stiff soil. This figure shows that the epicenter and focus. Now the thing is that what is epicenter? The vertical upward point on the focus where the earthquake generates below the surface of earth. Vertically upward point there will be called as epicenter, and where the earthquake generates is called a focus point, also known as hypocenter. These waves are called seismic waves, and these denote that how these waves interact with different man-made structures. Like in cities we have tall buildings, and then we have industrial areas, then we have bridges. All these structures are damaged by these seismic waves. These seismic waves are generally sine waves which have a graph of 1, 0 and -1. Moving further, we have ground improvement. Now this is the part where a site engineer or engineer in hold who have to decide that whether there are conditions for the ground improvement, whether he has to take steps to improve the ground, and he has to follow these two situations. Number one, if the ground condition at construction site are very poor, that need to dealt in very technical way. Number two, the ground at site may be rock or soil or alternating layer of this material. So accordingly, we need to understand the concerned problem. Moving further, we have then rock improvement. Uh, you will say that how there will be improvement in rocks, but we have certain positions where the rocks are also weaker because they have faults and folds in it, and when dealing with the tunneling aspect or tunneling building point of view, we have to consider the rock improvement also. While dealing rocks, we may face landsliding, extensive jointing, presence of severe folding and faulting in addition with flooding due to nearby stream or river. Soil improvement. Soil improvement can be by many ways, can be achieved by many ways, by densification of the soil, or to remove the excessive water in the soil. When there is excessive water in the soil, there will exist a condition called liquefaction, and liquefaction generally means that soil has excessive water and it flows like a slush. And then we have excessive pore water in the soil, and these two situations lead to the unstable structure, unstable building of the building structure on that type of soil. Soil improvement can be achieved by densification of the soil or improvement of its drainage capacity. Now these are the ways how to improve the soil, or how to improve the rock on which we have to made our on which we have to build our structures. Number one, removal and replacement. Removal and replacement generally denotes that when there is a soil not having a good bearing capacity or having a slushy material, or having or have enough liquefaction, we go for removal and replacement. That we brought an excavator and remove the soil layer which we don't want to need, and then replace it. Then on the second, we have a different situation called preloading. Preloading generally refers to have a load on the soil, and it will improve the soil by densified it, and we will achieve a greater densification by preloading. Number three, vertical drains. Vertical drains generally refers to the drains that are provided in the soil or in the rocks to provide a good drainage. Number four, in situ densification. In situ densification means to achieve the densification in the field. This can be achieved by different compaction rollers or sheaf foot rollers according to the situation on the sites. Number five, we have grouting. Grouting generally refers to the drilling of the drilling in the mountains or drilling in the soil to pour the concrete, having stabilization and mixtures to make the ground conditions better and to be to use it and to be useful in the further building constructions. Number seven, we have reinforcement. Reinforcement generally means that driving nails into the mountains to have stable to avoid the faults and folds, and to have a stable rocky strata to make our man-made structure. These figure shows the design stability, that how how we have to put our foundation so that we have achieved our design stability. Now this is a most important aspect we may counter in our life, where we have to avoid soft story ground floors. Now what are soft story ground floors? A soft story refers to a building ground floor that is significantly weaker than the floor above it. This can be due to many reasons. I will discuss a few. Number one, large openings for windows, doors, or garages. Number two, insufficient column spacing or inadequate column design. Number three, we have inadequate shear walls or bracing. These are the conditions due to which we have a soft story, and we must avoid these soft story ground floors. This figure shows that the remedial measures for soft story, this building have large, if we have to make it more stable, then we have to provide largest size tilt columns. We have to increase the size of these columns. If we want to make it more stable, then we have to provide bracing. Bracing means to connect these columns with each other, interconnected columns called bracing. This figure shows the bracing. This figure shows the RC wall, shear wall. We have, if we want to make our building more stable and less prone to the earthquake, and provide our building with earthquake resistant structure, then we have to provide a shear wall, reinforced concrete shear wall at the corners. Number four, this is a good approach, providing brick infills between the columns, that if the column size is not suitable and we have to retrofit it, then we have to provide some large brick infills between these columns. The hints, they avoid the weak links. I have discussed it before that when we have weak link in a building, it will topple over. Weak links refer to components or areas that are more vulnerable to failure or damage compared to other. As you may see that these areas have not a good good connection with the upper building. If we have a bracing here, then we have a good connection, but when a seismic wave came, it will topple over if it is not designed properly. This is a detailed view of the picture shown before, when we have a soft story in the middle, that it will topple over like this. These are the man-made structures. These are the skyscrapers, which are made in the past and are the most stable structure, like pyramids. Pyramids are made 100,000 years back, but these are the most stable because they have a good base and their top is not too much heavy. So there is a hint, when you have a great building structure, when you have to make a highest tallest building, then you have to provide means that you don't have to provide a greater or heavy top on the building. This is an earthquake disaster shown in the picture in the Bhuj. It is located in the Gujarat, and it came approximately, according to my information, in 1999, and these water tanks collapsed in the building. Now I have to inform you a most important thing in these water tanks. Water tanks on rooftop can pose several risks if not properly designed. Because when the earthquake shakes the structure, the water in the tanks generate waves, and if those wave frequency match with the seismic waves, then it will be a situation called resonance. Resonance amplified the waves and increase the water pressure on the tank walls. Resonance increase the water pressure on the tank walls, leading to failure or collapse. Thus, we have when we want to design a water tank on the rooftop, then it will be really careful about the design, because these structures can have a bad effect, or these structures can pose several damage due to earthquake. This is another example of earthquake when the design is not good. All the upper floors weak in long direction means these floors are not jointed well with the base, so they slide. This is an example of Izmit, Turkey, 1999. Now here is also an important concept: design for lateral forces. We have lateral when we design our building, we have different lateral forces. Number one, wind. Number two, seismic waves, and these two are the most important lateral forces. When we have to design our building, then we must consider the placement of the columns. We know that the columns are weaker when it is placed horizontal, and stronger when we place it vertical, like this in vertical position. So when the lateral forces in if we see this figure, if the lateral forces came from this side, uh, these columns will not will made a shear wall or have a less effect on the building. Will These columns will protect the building from these lateral forces and have a little impact on the building. But when the lateral forces came from this side, then these columns will slide and fall from its sides and have a greater damage. Now looking at this side, uh, when the lateral forces came from this side, then we have a great protection here because of the column placement. And when the lateral forces come here, we have a greater protection from here too. Then this structure will be considered as a strong structure. The design lateral forces specified in a standard shall be considered in each of the two orthogonal horizontal directions of the structure. Then we have a minimum column size, which is 250 to 300 millimeter of concrete. It is an example shown in the figure of insufficient lap length in RC columns, upper columns simply pulled out. When we don't provide enough lap length, then insufficient lap length lead to a bad leads to a bad structure, because these reinforcement rebars will have a lack of bond strength between the reinforcement bars and the concrete, and it will slip from its place. This is also an example of Izmit, Turkey. In 1999, the earthquake came, and when the structure damaged, we have seen that the hoops, which are these rings, are far apart. It is a heavy building. In a heavy building, we have to reduce its size. We have to reduce the center to center distance in between these rings, but these are widely spaced, and the hook they have is of 90 degree instead of 135 degree. This is a critical information. Then these are the essential elements for earthquake safety. We have to provide lintel band, roof floor band, vertical reinforcing bar at corner, door, window, plinth band, window sill bands. Torsional failure. Torsional failure means a twisting failure. Torsional mean a twisting. Torsional failures are seen to occur where the symmetry is not planned in the location of the lateral structural element, as for example providing the lift course at one end of the building or at one corner of the building, or unsymmetrical planned buildings in L shape at the street corners. These figures shows the pounding damage of adjacent buildings. This is also an important concept. When there are multi-story buildings, we have to provide some space between them, because if we don't provide space, we will have a condition of resonance, as I have mentioned it before, that when the resonance when there exists a situation of resonance, it will amplify the waves. And when the earthquake came and these buildings have interconnecting each other, and these buildings will have a resonance condition, these waves will amplify and have a greater damage to these structures. These are enforcement of earthquake safe construction, that we have to ensure these things to have a good check on our construction. Number one, capacity building of architects and engineering by education and training. Upgrading building bylaws for mandatory following of safe building codes. Mandatory design check for all tall buildings and special or critical lifeline buildings. Mandatory construction quality checks, fixing legal responsibility on buildings and professionals for safety of the buildings under future earthquake during a period of 50 after the construction. Shake table is also used to check the stability of the structure. Uh, to check the to check the placing of the columns in the structure. Shake table is used to test the response of a structure to see how they will held up in earthquakes. This is also an important concept. We have seen it in many structures. This bond is called a Koita bond. As we know that Koita is a seismic active zone, and they have seen Koita has seen many earthquakes in its history. Very dangerous and powerful seismic waves hit the structures and damaged all the buildings made by man. Then they introduce a good scheme. They used hollow blocks along with rebars introduced in them, and then they pour concrete in the edges to make the sides stronger and edges stronger to have greater stability in the structure. Then it is also an example of the Koita bond and using the rebars in hollow blocks. This figure shows that how the remedial measures or protective measures can be taken to have a good structure having a greater stability in seismic waves region or seismically active region. Then it is a great or important concept of base isolation. Base isolation are designed where the bottom portion of a building absorb the seismic shocks to prevent damage, and this concept was used as far back as the Mausoleum of Cyrus. This concept is taken from the ancient Egyptians and ancient Romans. They used to have a good base isolation to protect the upper structure laid on them. Base isolation can be done in many ways. Having a isolated building, base isolation bearings can be used. We can use spring with damper base isolator absorb the seismic energy of the earthquake and reduce structural damage. These springs absorb the seismic waves. This is an also example of the base isolation. These are the skyscrapers which have used the technology of base isolation. What does a steel frame building look like? Generally, a steel frame building have a column structure, column and base structure. The main load of the building is transferred on the columns and then to the base and not on the partition walls. How do we build a team? We have to build a team to have a good connection with each other, to have a beneficial effect in the form of construction of these structures. This example is of the column bracing. We have seen these interconnected columns, and the base is also interconnected, having a good and stable reaction when the seismic waves hit these structures. Now, tune mass damper is a technology, or it is we can say that it is a massive giant structure used in Taipei 101, which is the tallest building from 2004 to 2010 in Taiwan. This building was made in the period of 6 years, and they have introduced a tune mass damper which is of 1% of the total weight of the building. Means this tune mass damper is a massive giant structure having a weight of 660 tons, and it act as a counterbalance or provide a counterbalance along with the hydraulic dashboards like mega shock absorbers. The main thing is that they introduced this Taipei 101 tune mass damper at a height of 350 meters, 87th floor. This is a visual example of tuned mesh damper. This is an example how they use the tuned mesh damper and provide a shock absorber at its sides, that when the seismic waves came, the shock absorber absorbed those waves and uh, prevent the building from damage. Do masonry and steel frame buildings behave differently under earthquakes? Yes, the steel frame buildings behave differently under earthquake than the masonry, because in steel we have flexibility, and in masonry structures we don't have flexibility. Thus, the flexibility can absorb the seismic waves, and it will provide a lesser damage to the structures where they are used. Whereas in masonry structures, they are rigid structures. They don't have any flexibility, and when the seismic waves hit the masonry structure, they will have cracks in them, leading to the great destruction. What happens to masonry in earthquakes? It breaks, and they break badly. These are the figures shown that how masonry structures are damaged in seismic waves. This is a column failure. We can call it a buckling failure. When the load came, it generally opens the rebars in it. These building skeletons are flexible, they can bend. Steel buildings stands. Seismic isolation. This is also an example of the base isolation, where we can use different isolators like rubbers, like springs in the base of the structure to avoid the damage provided by the earthquake and the seismic waves. These are the expansion joints provided in the bridges, where if there is a movement, then these joints are flexible enough to have a little movement in the bridge and have a less damage to the bridge structure. This is Trans-Alaska oil pipeline, where it crosses the Denali Fault. It's designed to move 20 feet laterally and 5 feet vertically. This is a example of how the engineers cope with the problem of earthquake seismic region, earthquake active region, where the fault line crosses, and they have to place a pipeline there. They have made it. They have designed it in a way that it can move 20 feet laterally and 5 feet vertically. These are the figures shown that how the nuclear reactors are built and how the nuclear reactor is designed. Because if the nuclear reactors break, it would have greater damage to all of the mankind and to the surroundings and ecosystem. It is our intelligence, awareness, technical skills, and mastery to our profession to respond earthquake in better and safe way.